Hello, good morning. Am I audible? Hello.
Yes, sir.
Huh? Okay, so good morning and welcome to lecture on advanced power electronics. Yesterday we discussed a single phase dart bridge and load on the dart bridge. One case is a resistive load, second is RL load, and third is the RC parallel load. And we have seen it here. This particular slide shows whenever load is resistive, our source current is when load is resistive, we have seen that our source current is the sinusoidal one. Okay. Then we also discuss how to find out the ripple content in the output voltage of single phase dart bridge, and for that we want to know the RMS value and the average value of the waveform. Once you know the average and RMS value, you find out form factors, and a ripple factor will be given as a square root of form factor square minus 1. Then this is the particular uh, screenshot, particularly we obtained with the help of MATLAB. We are using Power GUI to find out the THD or FFT analysis. And this waveform is the source current waveform of dart bridge with R load. And we see that source current is almost sinusoidal. So THD is around 0.98%, less than 1%. Then after that, we discuss about the dart bridge, which is we are using a capacitor for filtering purpose, and we are using a resistive load, and in this case we have shown this is the voltage across the capacitor, and because of the voltage across the capacitor, our diodes, in case of resistive load, they are conducting for 180 degrees. Now in this case they are conducting for a very short duration, maybe 70 degrees to 100 degrees, and because of that our current is not a continuous one. We are having one positive pulse, then zero current, and then we are having a negative pulse. This, and particularly for this also we done the MATLAB simulation and find out the THD is comes out to be more than 230 or 229.57. Similarly, whenever our load is RL load, then our DC current is smooth and ripple free, and in that case our input current is the a square wave. So whenever load is RL, we are having a square wave, and for that square wave current, we can find out the THD. Now after that, we have just discussed about the harmonics, and we have find out the relationship between three currents. One is the RMS current, you can call as the total RMS current. Then fundamental component, RMS value of fundamental current or component, and the RMS value of harmonic. And relationship between is IRMS square will be I1 RMS square plus IH RMS square. But in the particular calculations, we can find out the IRMS and I1 RMS, and from that we find out IH RMS. And we are using here how to find out the fundamental component, or how to find out the peak amplitude of any harmonic when we are having a quarter wave symmetry. When we are having a quarter wave symmetry, we are getting an, that is the peak amplitude of nth harmonic, will be 8 by 2 pi integration 0 to pi by 2 f theta cos of n theta d theta. So this particular expression we can use for finding out the amplitude of nth harmonic. It may be a fundamental, maybe a third, maybe fifth. Putting the appropriate value of n, you get the all harmonic spectrum. Out of that, we can just put n equal to 1. So you will get the peak amplitude of fundamental, then divide it by root 2, you will get the RMS value of fundamental. Once you know the RMS value of fundamental and the RMS value of waveform, we use this expression I square will be I1 square plus IH square, and from that you find out IH, and our THD will be given by IH by I1 into 100. And now we have done the exercise for the square wave, and particularly we have to integrate the function from, we have to take a quarter wave symmetry, so that we have to shift the center at the 0 at the center of this waveform, and we have to integrate from 0 to pi by 2 to integrate. And during this 0 to pi by 2, we have seen that our function is having a constant value, and constant value will be equal to idc, and cos of n theta d theta. So we use this expression. Okay, just solve this and put n equal to 1. You will get the peak amplitude of fundamental. It is 4 idc by pi. The peak amplitude of fundamental, you divide it by root 2, you will get the RMS value of fundamental component. Once you know the RMS value of fundamental component and RMS value of the waveform itself, IDC is the RMS value of this waveform, and this is a RMS value of fundamental component, and from that we find out the RMS value of total harmonic IH, and IH by I1 you will get 0.482, means the THD, total harmonic distortion of the square wave, is a 48.2%. So this much part we have studied. Any question? What we have discussed last time? Am I audible? Hello?
Yes, sir.
Yes. Okay. So any question on this? So what is our conclusion? Can anybody tell what is yesterday's lecture's conclusion? What is conclusion of yesterday's lecture? In one line. Anybody can tell? Hello? What is our conclusion? A source current of diode bridge depends upon type of load on the diode bridge. If load on the diode bridge is resistive, our source current is sinusoidal. If the load on the diode bridge is highly inductive, RL load, then source current is the square wave. And third, when load on the uh, single phase diode bridge is a parallel combination of R and C, then we have seen that we are getting a positive pulse and negative pulse. That type of current we can obtain. Okay, and we have seen that this is what we are having a square wave. We have shown it here. Okay, so this is square wave, and the voltage and current for resistive load. So current is our, sorry, this is for RL load. A square current wave is the square wave, and it is in phase, you can call it in the voltage. So our Vs will be the voltage waveform, and Is is the source current. This is for diode bridge, or diode bridge also you can call as, that bridge also you can call as alpha equal to 0. A full control converter with alpha equal to 0. Alpha equal to 0 is nothing but the dart bridge. And here we use our expression of AN, what we have just shown it here. Okay, AN. Okay, we use this, put various values of n. We have seen that if you put n equal to 2, this is sine of pi, n equal to 4, sine of 2 pi. So that values will be 0. So here we can say it here, our even harmonics are absent. And so whatever harmonics present in the square wave, this is our, what we are having a square wave. This is our square waveform for which we find out the harmonic spectrum. What is meant by harmonic spectrum? So we can find out what harmonics are present and what is a magnitude of these harmonics. And we have seen that in the square wave, all odd harmonics are present. So it is third is there, fifth is there, seventh, ninth, 11th, 13th, and so on. All odd harmonics are present. And we have seen that third harmonic is one third of fundamental. So fundamental we assume as a 1 pu or 100%. Then third harmonic is one third of fundamental. Fifth harmonic is one fifth of fundamental. Seventh harmonic is one seventh of fundamental, and so on. Okay, so it will be a square wave is rich in the harmonics. Now some waveforms. Now with simple waveforms we can find out with the help of our equations, but waveforms are complicated, or it is very difficult to represent with the help of equations. Then we can take the help of MATLAB simulation. So we can use the MATLAB simulation for finding out the THD. So we okay, we are suppose we are going forward to want to find out the THD of source current of diode bridge. So very simple, you can just take the four diodes, take the source, construct the circuit, and connect the scope to the source current of which we want to measure the THD. So very first step is connect the scope to the waveform for which we want to obtain the THD. Then once you do that, then you make the setting in the scope that okay, or save the data in the workspace. That option is available in the settings of the particular scope. Once you simulate this with this, then you have to use the power GUI. If you click on power GUI, then we are having a FFT analysis, and go to the block, and from that we can find out the THD with the help of MATLAB. So have you done this job already? I think how to find out the THD. Am I audible? Hello.
Yes, sir.
Yes. Have you done this with the help of MATLAB simulation? This
Yes, sir.
type, how to find out THD with the help of MATLAB simulation?
Yes, sir. I
Oh,
have done it.
okay. So we are having now particular experiments. We will do this in the experiments. Now, with the help of the same, so we have just taken the screenshot of this. How to obtain this? We have just discussed single phase diode bridge R load, and you are knowing our current is almost sinusoidal, and THDs comes out to be a, this is the scope it will be given. The fundamental 50 hertz is the fundamental, then 150 is third, 250 is fifth, and so on. So we'll get the, this is the harmonic spectrum, and take total THD. So this scope will display one is total THD in percentage, and this total THD in percentage, if you see it here, it is a 0.98%, and a particular simulation, what is the peak value of fundamental. This will indicate the peak value of fundamental. All these particular harmonics, they will indicate the peak value of a fundamental. Okay. See, then we have gone for the RC parallel load, and then we have seen that we are having one positive spike. So here we are having one positive spike. If you see it here for positive half cycle, negative half cycle, negative. So our current is discontinuous. Okay, so particularly if you see this is our, and we have seen that if you find out, very difficult to find out the analytically how much is the THD content in this. It is again all harmonics are present, all odd harmonics are present in this case. We use a MATLAB simulation, and we find out particularly this THD for this waveform. Whatever we have shown is comes out to be a 229.57%. So whatever the waveform you are seeing, for that we are having THD is almost 230%. Okay, so that is a very very high THD in case of this. Similar, we can go for RL load, highly inductive load, and we have seen that our current is the square wave. Okay, and for a simple we are square wave, we have done the analysis now. Is it right? We are analytically we have find out this expression, and THD is contained to be 48.2%. Now we see with the MATLAB simulation how much value we can get. So if you see it here, this we are done for MATLAB simulation, the square wave, and here almost we are getting a 48.12%. So THD in the source current. So calculated, and this will be a perfect, particularly for a simple waveforms. Easy to represent with the help of mathematical equations. So square wave, THD of the square wave is almost 48.12%. So this is all about we are having for a diode bridge. Now this is the exercise you have to do. So we are having, so you have to determine the THD, which use the expression for AN and find out the RMS value. So this is the first exercise. We are having, this is 30 degrees, 0 to 30 degrees 0, then 30 to 150 we are 120 degrees positive current, constant value equal to VDC. Then next 60 degrees we are 0, again this waveform we can call as quasi square wave. Okay, this waveform we can call as a quasi square wave, and for this waveform we want to find out THD. This is one exercise you have to do. So you have to take the 0 at the center of this. Okay, you have to take this 0 will be at this position. This is 0. Okay, and then this will be come out to be a 60 degrees. So it will be a pi by 3. So you have to integrate function only up to pi by 3. Pi by 3 to pi by 2, it is a 0. So this particular expression, we have to integrate. An expression, you have to integrate. What is our integration limits? It will be from 0 to pi by 3. So it will be 0 to pi by 3. We have to integrate the expression for an. So this is, and we have to use the formula. So this is clear. Is it clear how to solve this problem? Am I audible? Hello. Your response is required. Hello. Am I audible?
Yes, sir.
Yes, sir.
Yes. So here we are having this is a cos square waveform, and we are having we have to make the 0 at the center of this, and we have seen that 120. So it will divide by 2. It will 60 degrees. So our integration limits will be 0 to 60, 0 to pi by 3, and pi by 3 to pi by 2. We are having 0, so not necessary to go for this. This we can do it here. Whereas here, if you see it here, the second waveform, it was somewhat complicated one. Okay, so we can put the 0 here, and 0 to pi by 3 we are having a constant function. Okay, and pi by 3 to here it will come as pi by 2, and pi by 2 we write the expression for the line. Okay, we write the expression for line. So pi by 3 to pi by 2, a particular this period, particularly this period, you have to write the expression for line, and then use the same formula up to 0 to pi by 3. It will be same, and pi by 3 to pi by 2, you write the expression for the line and use this particular this to find out this. So the second problem is somewhat tricky. It will require more time, but definitely you can try for this. So the second problem. And third problem is, again we are having a width is 90 degrees. So here you can take a center at the 45 degrees. Okay, here this is our 0, and then you have to integrate only pi by 4, 45 degrees. Okay, we have to integrate only pi by 4, because up to pi by 2, pi by 4 to pi by 2, it is a 0. So we have to just integrate now. In this case, our integration will be just from 0 to pi by 4. Okay, so that integration limits, and value is the constant plus IDC. So these are the three waveforms for which this is exercise you can do. Is it clear? Hello, is this clear?
Yes, sir.
So you just try it, and you have to give me the answers. Is it possible on Wednesday, next Wednesday's lecture? Okay, so next Wednesday's lecture, your answers should be ready for this. And now let us, so we done now. Now we can go for, on the similar basis, we can go for single phase full control converter. We are not taking a full course. Okay, we are hurriedly going it. It is requested to take this. Okay, you can read update about the power electronics. Okay, so now we are going for a single phase full control converter. We have just discussed diode bridge, and now we are going for single phase a full control converter. So single phase full control converter, all devices we are having is the thyristors. All four devices are the thyristors. Now you are knowing the this full control converter works in the two quadrants. Is it clear? Full control converter with RLE load. Our load is RLE. We are having the DC side also. We are having a battery or DC source. Then we have seen that this full control converter works in two modes, and these two modes, one mode we can call as, what are the two modes of full control converter? Anybody? What are the two modes of full control converter?
Rectifier and line inverted commutator.
Okay, so we are having, one is a rectifier. A rectifier means our VO IO both are positive. This is the conventional direction. Plus this is the VO is a positive VO I have marked, and this is the IO is the positive IO is this direction. This is our positive IO. When both are positive, VO is positive and IO is positive, this is our first quadrant. Is it clear? When both output voltage is positive and output current is positive, I have shown the convention for positive current. Okay, I have shown the convention for positive current. This will be positive current. We have marked IO, similar the polarity of VO. When both IO and VO are positive, so this is our first quadrant operation, and this we can call as current is flowing from AC side to the DC side. This is our what operation we can give the name to this. A first quadrant operation. What name we can give to it? What is the name? We are converting this AC. Now power is flowing from this. This is our first quadrant. Power is flowing from AC side to the DC side. Power is flowing from AC side to the DC side, and this operation you can call as rectifier operation. This we can call as a rectifier operation. It is very difficult to write me. So this is our rectifier operation of first quadrant. And now another option is there. We'll discuss it afterwards. But in case of rectifier operation, what is the range of alpha? We'll just now discuss only a first quadrant operation. After completing this, then we can go for a next quadrant operation. So this is what I hatched is our a first quadrant operation, and this is called as rectifier operation. And in case of rectifier operation, power is flowing from AC side to the DC side. Our converter is converting AC power into the DC power. This operation we can call as a rectifier operation. For that, our load requirement is, let us assume that RL load. What is the range of alpha for this first quadrant operation? Hello, what is the range of alpha for the first quadrant operation?
0 to 90 degrees, sir.
0 to 90 degrees, correct, very well. So range of alpha is 0 to 90 degrees. It will work in the rectifier mode. And now we have shown that our load is RL load. It's just we have shown a load as a square block, but it is our load is RL. So how is our DC current? Our DC current here, whatever IO or DC you can call it, IO or IDC, whatever you can call it. This IO is how it will be a smooth and ripple free. Why it is smooth and ripple free? Because we are having the RL load. We are assumed as the RL load here, a resistor and inductive load. So our IDC is smooth and ripple free. Our IO is smooth and ripple free. And this IO, you have seen it here, it will be represented here. This is the IO. It will be a smooth and ripple free because of RL load. And now here we have seen that in case of full control, here current is smooth and continuous. So T1 and T2 are conducting simultaneously. And when T1 and T2 will turn off, let us assume that this is the first period. Here we have shown it here. Let us have use. When T1 and T2, let us assume here T1 and T2 are conducting. Once T1 and T2 are on, they will turn off when T3 and T4 are turned on. Means each device, whatever may be alpha, each device conducts for a period of, in case of
5 radians.
180 degrees. Is it clear? Each device. So T1 and T2 will conduct. To turn it off, we have to turn on T3 and T4. To turn off T3 and T4, we have to turn on T1 and T2. So here, each device, whatever may be alpha, alpha is 0, alpha is 45, alpha is 60. Okay. So each device is conducting for a period of 180 degrees. So here we have shown it here. The alpha, maybe you can assume it as around 30 degrees. We apply the pulse and you will get the output voltage. And this T1 and T2 will continue till T3 and T4 are on. Okay. And that's why our output voltage will also go towards the negative side. And this is the output voltage waveform. Okay. This is the output voltage waveform. Whenever alpha is 30 degrees, is it right? It will have some negative value also. So this will be depending upon alpha. When alpha is 90 degrees, we have seen that average voltage is 0. Average voltage is 0. And this is conducting for 180, each device conducting for 180. So our source current is the square wave. You see it here. IT1 or thyristor 1 is conducting for 180 degrees, so positive current, T1 and T2. T3 and T4 conducts, then our source current will be negative. So this is our source current. So here our source current, this will be a source current. What you can say? A source current is a square waveform. Is it clear? A source current is the square waveform. Is it clear? Hello.
Yes,
So
sir.
this is our rectifier operation. A range of alpha is 0 to 90 degrees. Power is flowing from, this is our AC side. Okay, this is supply side, AC side. Power is flowing from AC to DC. And we have seen that our expression for output voltage. What is expression for output voltage? Our output voltage expression, can you recall? Output voltage will be twice Vm by pi, twice Vm by pi cos of alpha. Okay, so that will be our expression cos of alpha. Is it clear? Twice Vm by pi cos of alpha. That will be our expression. When alpha equal to 0, what is meaning of alpha equal to 0? Hello, this full control converter, if I make alpha equal to 0, the configuration will be
same as diode bridge rectifier, sir.
same as diode bridge. So alpha equal to 0 and put a cos of alpha, alpha equal to 0. So for diode bridge, our output voltage is twice Vm by pi. So that will be our output voltage. That will be equal to twice Vm by pi for the diode bridge. And now here, if you put alpha equal to 90 degrees, what will happen? Cos of 90 is 0. So output voltage will be 0. So output voltage is maximum when alpha equal to 0. Output voltage will be 0 when alpha is 90 degrees. And you are knowing this is the expression for power factor. Power factor in case of this power electronic circuit, we are giving distortion factor multiplied by displacement factor. And particularly for full control converter, our power factor single phase, this is twice or 2 root 2 by pi cos of alpha, where 2 root 2 by pi we can call as a distortion factor. Can you recall a distortion factor? Term of the distortion factor. Can you recall? A distortion, how we define the distortion factor? I1 upon IRMS.
Yes, sir.
Fundamental to the RMS value. That ratio we can call as a distortion factor, and displacement factor is same as cos of alpha. Okay, so is it clear? This is the rectifier operation. Power is flowing from AC side to the DC side. Range of alpha is 0 to 90. Our input current is the square wave, but this current will shift. Okay, this current particularly will shift as alpha increases. This current will shift in this direction. Okay, voltage and the shift will be present between the voltage and this. So as alpha increases, power factor decreases. What is power factor of circuit when alpha equal to 90? What is power factor of the circuit when alpha equal to 90 degrees? What is the power factor of the circuit? So cos of 90 is 0. So power factor is 0. Is it right? Power factor is 0 when alpha equal to 90 degrees. Power factor is 0 means it takes power, but that all power is the reactive power, lagging reactive power. I think, is it clear? Rectifier operation of full control converter. Is it okay?
Yes, sir.
Yes, okay. Then we can go for next inverter operation. Inverter operation, here load we require, I will just draw it load here. In that case, we require RLE type load. First is we require R, then we require inductance, and then here battery polarity is very, very important. This is our battery polarity. This battery polarity, I will say instead of load, you can see this will be our circuit. Okay, you neglect this. Okay, you can make this. So load will be our like this. We are having R. Okay, then we are having L, and then we are having a E. And the polarity of E, you just see it here. Polarity of E, and the direction of current is never changing. Why direction of current is not changing? Here we have shown it here, a direction of current. We are going for the inverter operation. But our IDC direction of current is not changing. What is the reason? Our direction of IDC or direction of DC current, it is always the downward what we have shown it here. The direction remains same and reason lies in the
Thyristor operation, sir. It cannot conduct
devices
separately.
are unidirectional. Thyristor is conducting the current from anode to cathode. This is our direction of current. So devices are unidirectional. Current in the devices is flowing only in one direction. That is the reason. So our IDCs remain unidirectional. Okay. And now here, because IDCs remains unidirectional, but now our output voltage will reverse the polarity. So here, in case of rectifier mode, we have seen that upper terminal is positive, lower is negative. But inverter, we have shown now that this lower terminal will become positive and upper terminal will become negative. When alpha you increase above 90 degrees, when you increase alpha above 90 degrees, our polarity of output voltage will change. And that's why we have shown that here current will be remaining positive as it is, but voltage will be a negative. This is fourth quadrant operation. This is a fourth quadrant operation we will get. And reason is our voltage polarity will reverse, but current is not reversing. So either one polarity is reversed, then now power flow will be from DC side to the AC side. This case, our power is flowing from DC side to AC side. It means that our this battery, this is what we have shown, battery supplying power to grid. Is it clear? Now in this case, our battery is supplying power to the grid. Means we are discharging our battery into the grid or into the supply. Is it clear? Here when alpha is greater than 90 degrees, a firing angle is greater than 90 degrees, and load what we have shown it here, RLE, a polarity of E is such that it will support the current, DC current, polarity will be such that support the DC current. And then when alpha is greater than 90 degrees, we have shown that the polarity of this converter will reverse. So lower terminal will now become positive, upper terminal will become negative. Now, how to find out the magnitude of IDC? This voltage you can call as VDC. Let us assume that this is a VO. Okay, symbol already is there. So VO. So once you know the VO, once you know the E, how we get the IDC value? Anybody? How we get IDC value in this case? IDC will be equal to, now it is very simple circuit. This voltage VO is opposing. VO is opposing to the E. Who should be more? VO should be more or E should be more? For flow of current, IDC what we marked, and if you see the circuit, so which value should be more? Is it VO should be more or E should be more?
V0, sir.
V0, if V0 is more, then how the current will flow? Current has to flow which direction? Current has to flow this direction. Is it a battery from this downward direction? Or current has to flow like this, what I mark it here. And in that case, when current has to flow this way, then our E should be greater than V. Is it right? Very important. Sir. Our E should be greater than V, VO. But VO can be adjusted. How we adjust VO? How we adjust the VO?
By changing alpha, sir.
By changing alpha. So whatever value of E, we adjust the alpha so that VO can be made less than the E. And how will our expression for the DC current, IDC? It will be simple, E minus VO divided by R. Inductance is not, okay, inductance is just purpose to have a making the current smooth. So our IDC value, is it right? Whatever the IDC, whatever the current flowing, or IO, what we can call it here, this is IO or IDC, same, both are the same, IO call, or you can call as IDC. And how to get that value? That IDC will be equal to, our IO output current will be equal to E minus VO by R. And VO we adjust twice Vm by pi cos of alpha. By adjusting this, we can adjust this. So is it clear how the inverter operation takes place? What is essential things? We should have a active source at the DC side to maintain the DC current. Our polarity should be like this. If you reverse the polarity of battery, can inverter operation take place? If we reverse the polarity of E, inverter operation will not take place. For inverter operation, we should require three conditions. Firing angle should be greater than 90 degrees. So first case, a firing angle should be greater than 90. This is the first case. Firing angle should be greater than 90 degrees. Our current should be a continuous one. For that, we require a sufficient inductance in the DC side. And there should be battery, or there should be active DC source. Okay, active DC source, so that, and with a proper polarity, so that the polarity of battery is such that it will maintain the DC current. And once these three conditions are satisfied, our this full control converter will work into the inverter mode. And for that, our alpha should be greater than 90 degrees. Now, once this our waveforms are very clear now. So what is alpha here? Approximate alpha. It may be around 120 degrees. Let us assume that this is alpha equal to 120 degrees. So our now T1 and T2, if you see it here, T1 will start here. This is alpha. So this will be a particularly period where T1 and T2 are conducting. Is it right? This is the period where we are having a T1 and a T2 are conducting. 1 and 2. T1 and T2 are conducting this period. And other period, here we have seen that this particular period, you can, I am drawing with different color, this period or this period, a T3 and T4 will conduct. T3 and T4 will conduct. Okay. And here we have seen that T1, T2 conducts. What is our logic? When T1, T2 conducts, our source current is positive constant value. T3, T4 conducts, source current is a negative constant value. So here again, what we say, our source current is a square wave. Source current is a square wave. So our battery is supplying current to the grid, but at what wave shape it is supplying? It is not supplying a sinusoidal current to the grid. Is it clear? Our battery now in inverter operation, we can say here, inverter operation, our battery is supplying power to the grid. Am I right? In the inverter mode, battery is supplying power to the grid. Am I right? Hello. In the inverter
Yes,
mode, battery is supplying power to the grid. But what wave shape it supplies the current? The current is not a sinusoidal. It is not giving power to the grid at the sinusoidal current, but it gives power to the grid at square wave. So battery is giving a square wave current to the grid. Is it right? Square wave current to the grid. So any question on the single phase full wave full control converter? Any doubt? We discussed both operation, rectifier operation, inverter operation, what is essential for inverter operation, and very important conclusion is a source current of full control converter with RL load is a square wave, whether it operates in the rectifier mode or in the inverter mode. Source current of the single phase full wave full control converter is a square wave. Any question?
no, sir, no questions.
Okay, so let us go for now. So this will be, so what conclusion we are drawing? So this is the advantage or disadvantage of full control converter. It gives a square wave current or it takes a square wave current. Is it advantage or disadvantage of the rectifier circuit or converter circuit?
Disadvantage.
It is a disadvantage. It takes a square wave current. It means it injects harmonics. It pollutes the supply system. It is like a air pollution. Vehicles are making air pollution. Similarly, our converter is making our power system pollution. They are polluting our power system. So this is one thing. And what about, we have discussed also the power factor at which this converter works. If you see here, power factor at which the converter works. Power factor will be given as this single phase full control converter. Power factor is 2 root 2 by pi cos alpha. And here we have seen that alpha is 60 degrees. Power factor is very poor. 90, it is 0. So means it takes a lagging reactive power from the supply. Rectifier, whether it works in the rectifier mode, inverter mode, it always takes the reactive power. If you go for here inverter operation, and if you want to show the power flow, active and reactive power, then how we represent? So this power flow, what you can call it, what I shown with the red. Okay, power is flowing from DC side to the AC side. That power is our active power flow. P you can call it. This power flow is a active power flow. But though it is working in the inverter mode, it takes the reactive power from the supply. So if our Q reactive power, if I represent the Q with the reactive power, and now the reactive power will be flow this direction. So supply has to always provide the Q, whether it is to be operated in the rectifier mode or the inverter mode. Is it clear? Now in case of this inverter mode, supply has to provide a reactive power, whereas our battery is providing active power to the grid. So power flow, keep P and Q, they are in opposite direction in case of a particularly this inverter operation. Whereas here in both cases, P and Q flowing in both directions. Okay, in case of a rectifier, P and Q both are flowing in the same direction in case of a rectifier operation. Whereas in case of inverter operation, P is flowing from DC side to AC side, whereas Q is always flowing from AC side to the DC side. Is it clear? A power flow, active power flow and the reactive power flow in the converter. Is it clear? Active power flow and reactive power flow.
Yes, sir.
Yes. So now let us go for, again we are revising the things quickly. So now we can go for three-phase circuit, and we'll just today we discuss about the three-phase diode bridge. Okay. So we have seen that three-phase diode bridge, a number of diodes required are 6. So we are having, we mark, this is a D1, then we mark D2, D3, D4, D5, D6. So diodes are marked as per their conducting sequence. So here 1, 2, 3, 4, 5, 6. We mark as a diodes, we mark as a conducting sequence. Now what is conduction period of each diode? Can you just recall? Each diode is conducting for a period of how much duration?
60 degrees.
One.
How much degrees each diode conducts? Just recall
120
the
degrees.
things.
120 degrees.
So each
120
diode
degrees.
conducts for a period of 120 degrees. Is it right? So each diode is conducting for 120 degrees. And here sharing is between, out of these D1, D3, D5, one will be always on. Okay, the 360 degrees is equally divided by these three devices. Similarly, this 360 degrees is equally divided by lower this. Okay. So out of this D1, D3, D5, one device will be always on. Whereas D4, D5, sorry, D2, D4, D6, one device is on. So at a time, how many devices will be on? One from these three, upper three, one from this. So at a time, any two devices will be on. At a time, any two devices will be on, one from upper group and one from the lower group. How to draw the output voltage waveform of this circuit? Can you just recall how, if suppose I want to draw the output voltage waveform of this diode bridge, what procedure we can follow? So how we draw the output voltage waveform for this? What procedure we can follow? Anybody can tell us?
First, we draw line to line phase voltages.
Okay,
Of
line
both
to
the three
line
phases.
voltages. That is line voltages. Okay, we are
Yeah.
talking about the line voltage. Line voltage means ABC here. If you see it here, VABC. If are you getting? I think that we have shown it with 1 minute. So this is our A point. Is it recall? This is our A point, then B point. Okay, and the C point. So we want to first draw the VAB, VBC and VCA. These are line voltages. So first we draw 3 line voltages. Then invert these line voltages. Means how much? 3 original and 3 inverted. So we should know the 6 line voltages. Is it right? VAB inverted will be VBA. VBC inverted will be VCB, like that. So we invert the, so we are having 3 line voltages. What are these 3 line voltages? VAB. Okay. So one is VAB, then we are having VBC, then we are having VCA. Inverted will be VAC, VBC will be CB and BA. So we draw the 6 line voltages, and once we draw the 6 line voltages, okay, so here we have shown it here 6 line voltages. Okay, all these 6 line voltages. This is one waveform. I will just trace. Okay, this will be our VAB. Okay, it is very difficult, so I will be just drawing one waveform that will be a VAB. This is our one waveform VAB. Then 120 degrees, we are having another waveform that is a VBC. VAB, after that, this is a VBC. I am drawing, this is a VBC waveform. This is a VBC. And okay, so this is a VBC. And third waveform is VCA. I will draw black. So VCA, this is our VCA, 3 waveforms. This is VCA. And then you invert this. So total all 6 you will see it, and then upper envelope. So upper envelope of all these. So here, upper envelope of all this. This is our output voltage waveform. Is it right? So I'm just trying to show it here. This will be just, I am upper envelope of this. Okay. So this will be our output voltage waveform. Is it clear? So how to draw the output voltage waveform? So here we have shown it here. Okay, and now our interest is how to find out the source current waveform. How to find out the source current waveform. So here our DC current, again we are assuming here we have seen that dark waveform, output voltage waveform is almost smooth. A ripple content is very less, and so that RL load is there, then we can say our current, DC current, is almost smooth and ripple free. This is our DC current. This DC current, whatever this DC current flowing in the load, that will be our smooth and ripple free. A smooth DC current, we assume it. What is the conduction speed of D1? It conducts for 120 degrees. And when D1 conducts, how the current will flow? D1, it may be pairing with D2. D1, it may be sparing, sorry. So A, I have to make it correctly. So A is this. So when D1 is conducting, this is A, and return path is provided through a D2. To the D2. And when D4 is conducting, our current path will be D4 is conducting. So D4 is conducting, our current will be flowing like this. Okay, and this. So here a positive current when D1 is conducting, a negative current when D4 is conducting. Is it clear? What logic we are putting? When D4 is conducting, current will flow like this. Is it clear? When D4 is conducting, current will flow like this. When D1 is conducting, current will flow like this. Whatever we shown with the black. This. So here we can say that when D1 conducts, our source current is positive. D4 conducts, source current is negative. D1 conducts for 120 degrees. So source current is positive for 120 degrees. D4 conducts 120 degrees. So source current will be negative for 120 degrees. And in between period, our this A phase is not connected. Some duration where D1 and D4 both are not conducting. So the current taken from the A phase is 0. So is it clear? What will be a nature of source current of a three-phase diode bridge? What is the nature of
That's
source current of three-phase diode bridge? Once again, tell me.
square wave.
It is not the square wave.
Quasi square
120
wave.
degrees, a positive current, and and 120 degrees negative current. But in between, we don't have a current. Okay,
Quasi
because
square
whenever
wave, sir.
D1 is not conducting and D4 is not conducting, our current will be 0. So source current of a particular case will be something like this. Uh, 120 degrees, it is a positive current. Next 60 degrees, no current. Then next 120 degrees, positive current. Okay, and then 60 degrees 0, and then again 120 degrees a positive current. So this is our wave shape of the source current. So 120 degrees positive current, 60 degrees no current, because during this 60 degree D1 and D4 are not conducting and D4 is conducting, then current is the negative. So this is the wave shape of current. So on that what we have discussed it here. Before going to that, okay, what we are saying is each device conducts for a period of 120 degrees. But we have named the devices as D1, D2, D3, D4, D6. And here D1, D2. D1 is making a partnership with D2 and D6. If you write it in circle, okay, so we are having make it a circle and mark the devices. This is 1, okay, then 2, then 3, 4, 5, and then 6. So now here 1 is conducting 120 degrees but make partnership with 6 and 2. 1 is making a partnership with 6 and 2. So 1 and 6 is conducting for 60 degrees. 1 and 2 is conducting for 60 degrees. And 2 and 3 are conducting for 60 degrees. 3 and 4 are conducting for 60 degrees. 4 and 5 are conducting for 60 degrees. 5 and 6 are conducting for 60 degrees. So each pair D1, D2, what is the conduction period of D1, D2? 60 degrees. D2, D3, 60 degrees. D3, D4, 60 degrees. So this pair conducts for 60 degrees, but individual device conducts for a period of 120 degrees. D1 is making a partnership with 6 and 2. Now D2 is making a partnership with 1 and 3. Similarly, 3 is making partnership with 2 and 4. So like that. So each device is conducting. So each device conducts for 120 degrees. And now conducting sequence we have given. It is we mark at D1, D2, D3, D4, D5, D6. But the pair, so D1, D2 is one pair conducting for 60 degrees. Then D2, D3 is again a 60 degrees. So D2 is sharing with D1, D2 is sharing with D3. So D3, D4 conducts. So this pair conducts for a period of 60 degrees. And because of that, what we are having, this will be our nature of source current, supply current. Supply current of diode bridge is this waveform we can call as quasi square wave. This waveform we can call as a quasi square wave. Square. This waveform we can call as a quasi square wave. So what is our simple conclusion? Three-phase diode bridge takes a quasi square wave current from the supply. Is it clear? What is our conclusion in one line? What is our conclusion in one line? Anybody can tell me? Hello?
Three-phase source current follows quasi square wave.
So source current of three-phase diode bridge is the quasi square wave. It is a positive current for 120 degrees, negative current for 120 degrees, and 60 degrees zero current. That particularly we are having. And this is how to draw it. So this is our We have shown it here. This is our total load current. DC current is smooth and ripple free. Here we have shown that when A is positive, AP and AC, where A is maximum positive, so here our D1 is conducting for 120 degrees. Okay. Similarly, when D2 will conduct, when D2 is conducting, when maximum C is maximum negative in this case. So this is where I have shown the conduction period of D1, D2, D3, D4. And our source current IA, when D1 conducts, it will be a positive. So our D1 conducts, so this will be a positive current. And D4 conducts, it will be a, this is our D4, it will be a negative current. So this will be our, particularly we are having a quasi square wave current. This is for one phase. Similar will be the other phase having a phase shift of 120. So our very, very simple conclusion regarding whether load, a particular R load or RL load, both cases, when R load and RL load, our source current is a quasi square wave. Plain words we can say it here. Okay. So any questions now? Any doubts?
No doubt, sir.
Huh?
No doubt.
Okay. So let us meet tomorrow at again 10:15. Is it okay? As per your timetable? Tomorrow what time we have to meet?
10:15.
Okay, 10:15 tomorrow we'll meet. So any questions, any your problems? Is it you are facing some problems while listening, or his voice is not clear, or any other problems, PPTs are not visible? Is there any
No,
problem
no,
you are
sir.
facing?
No problem, sir.
Huh? Okay, thank you. So we'll meet tomorrow at 10:15. Okay, thank you.